This is Unit 2, Number 9. A long conducting cylinder of length L has a total charge plus Q and is surrounded by a conducting cylindrical shell having a total charge of minus 2Q as shown in the sketch. Using Gauss's law, find A. The E field at a radial distance r outside the shell. Okay, so for part A, we're going to imagine that we're like a point here and the distance is r, and we have to find the electric field. So Gauss's law states that the integral of E dot dA equals the charge inside divided by epsilon. So if we draw a Gaussian surface as a cylinder around that whole system, the field lines are in this case going to go inwards because the total charge inside is going to be negative Q and the field is always in the direction of the positive charge. So it's going to go inwards and it's going to pass through the sides of the cylinder but not through the top. So this integral simplifies to E times, and then the area is going to be the lateral surface area because that's where the field lines go through. So that will be 2 pi RL, and that's going to equal the total charge inside divided by epsilon. So the electric field is going to be Q over 2 pi RL epsilon, and as always we worry about direction later, so instead of putting on the negative sign at the beginning, we're going to say that this points radially inward, because like I said before, the total charge inside is negative Q, so then a positive charge will want to go towards it, so it goes inward. Part B says to find the E field at a point in the region between the cylinder and the shell. So the key to solving this part is to ignore the shell completely and to draw a Gaussian surface around just the cylinder. So we're just going to draw like an imaginary cylinder outside that cylinder, because the whole point of Gauss's law is like to ignore everything outside your Gaussian surface. So the total charge inside is going to be positive Q this time because it's just a cylinder. So the magnitude of the electric field will be the same, but this time it points radially outward because it's positively charged, so a positive charge wants to go out. So that's part B. And part C says to find the distribution of the charge on the conducting shell. So for this, if we have our system here of a cylinder and the shell around it, we're going to imagine, so we're going to draw our Gaussian surface like right on that shell. So like that really thin border between the inner surface and the outer surface. And basically because this is a conductor, the electric field within any conducting material is going to be 0. And like using Gauss's law, E dot dA equals Q over epsilon. If the electric field is 0, that means the charge also has to be 0 inside our Gaussian surface. So if we let W equal the charge on the inner surface of that shell, then we'd have, and then we know that the charge of the cylinder is plus Q. So because our Gaussian surface is like right inside that cylindrical shell, the total charge inside of our Gaussian surface is going to be Q plus W, and this has to equal 0 because that the charge is just 0 on the inside of a Gaussian surface for any conducting material. So we get that W equals negative Q, and then we know that the total charge of that shell is negative 2Q. So the outer surface also has to be a charge of negative Q for them to add up to be negative 2Q. So that's why negative Q is distributed on both the inner and outer surfaces of that conducting shell. And that is number 9.